Nice to see everybody. I can't see everybody that's in the session right now, but thanks for attending. I'm Graham Larson, AI and Technology Manager here at Verto, joined by Sare, my colleague, who's been working very closely with me on building out the core data capabilities of what is commonly known as Verto's digital twin. Um, so if we dive into things here, you may have heard of Verto in a few different contexts. Um, what we really do, though, and specialize in is the transformation of data from source. So that would be a point of care system like an EMR. Um, we ingest things like claims data, et cetera. Um, transforming transforming that to FHIR and standardizing it to common code sets, and also extracting a whole bunch of valuable information from uh, our natural language processing pipeline that helps us structure the unstructured pieces of the EMR. And the end goal is to present that data back in a variety of different ways. Mostly these days, it's to serve population health needs. So ignoring kind of the right side of that, there's a presentation tomorrow, if you get the chance to attend as well, where our solutions engineer Cho is going to be walking through how we do a little bit of that text extraction that I talked about on the downstream processing side. What Sari and I are going to be focusing on today is the left side of your screen, which is how do we get data out of a source system? What are some of the challenges with integrating with different EMRs, especially when you have to integrate multiple EMRs to create a single uniform patient record? And what are some of the strategies that we at Verto have used and applied to this problem to make things easier for us? So, over the past year and a half, we've integrated with um, almost every common EMR that exists in Canada, and a lot of them in the US too. And so from that, we've had to kind of develop strategies to make this more efficient so that when we do get a new integration and a new client to onboard, it's not a matter of months, but it's a matter of weeks or days to get that data flowing and to get them live on our solution. So with that, Sari's kind of handled a lot of the hands-on work in this space over the last year at Verto. So I'm going to pass it off to her to give you a kind of a breakdown of what we've seen as the main problems in the space. What are some of the challenges with having to integrate with various EMRs and even various instances of the same EMR? Some of the challenges we've had with that. And then some of the solutions that we've deployed to resolve those. So, sorry, go ahead, take it away.
Yeah. Hi everyone. Thanks, Cam, for the great intro and the end-to-end overview of the platform. As we saw in the previous slide, the very first step in the entire process is to standardize the diverse healthcare data into a standard FHIR conformant format. But as everyone in the call know, it's not as straightforward as that might sound, and the mapping to FHIR can be even one of the most time-consuming and tedious step in the entire process. And as a result, we found it valuable to highlight some of the real specific challenges that we found over the past few months of working with different Canadian and US EMRs, and how those challenges can lead to poor data quality in the resulting data. So in this slide, we can see some of those challenges. One of the most frequent one was the field use that that can be used differently from specialty to specialty and user to user. One example that they came across when I was working with one of the AMR's e-clinical workflow was for the blood pressure test results that was sometimes stored as a value string in the observation object in a ratio format like 120/80, but sometimes the same test was captured into different observation objects, like in terms of the systolic and diastolic pressure, systolic and diastolic pressure. And it shows that even within the same EMR, when the workflow differs amongst user, and therefore there can't be a one unified one-to-one mapping from the source data into the target FHIR object. The other challenge was about the wrapper resources, more specifically the document reference. Another example about that is that like we were looking specifically for some referrals to some specific cancer screening tests. So the very first object that usually I'm thinking of is the service request. However, in that specific EMR, the data wasn't populated in service request. And when we looked deeper into the source data, we noticed that those referrals are actually recorded in their original form format, and then they are dumped into the document reference resource as a consultation note. And then basically the document reference is using as a catch-all object to store referral notes, history, HMP notes, progress notes, and different types of notes, which also shows that the FHIR conformance doesn't really translate to data quality. And most of the time, the important data is often left in unstructured resources. The other challenge is about the resource use, and because the FHIR definition is broad enough that different vendors may use one FHIR resource for different purposes in order to capture the same clinical event. Another example about that is the preventive screening tests that are usually stored as CPT codes inside the procedure object, but inside ECW, we were seeing that those specific events were captured as a visit type within the encounter object, which is also a correct way of storing data, but also proves that the resource use remains pretty flexible across different EMRs and practice by practice. Last but not least is that the true conformance is rare, and in practice, FHIR compatible APIs sometimes only meet the surface level structural requirements, and there are semantic inconsistencies and workflow driven misuse of resources, which can significantly degrade the data quality and also increase the mapping effort. Some examples about the conformance issue is that like Oscar EMR were using we're capturing preventive procedures in an immunization object, which is like not the correct way of doing that, or sometimes it was violating the cardinality according to FHIR, or the most supported fields weren't populated 100% of the time, or like sometimes the condition status are remained as active even if they are resolved, which is also like showing that many of the FHIR APIs would fail a true conformance test and leaves many of those discrepancies up to the downstream applications to resolve. So now that we've better understand all these challenges, we were thinking of how we can address some of those challenges and also tackle with them and improve our mapping process. And the solution that we came up with was to build an automated data profiling step into our entire pipeline. What do we mean by an automated data profiling? It's like a data-driven suggestion SDK that compares the field characteristics like the type, distribution, value sets, or other characteristics to identify probable mappings between the source and the target fields. The main feature of this automated data profiling is shown in this slide. So one of the feature is that it shouldn't be only limited to be to the API sources, but it should be also capable of running on any other data sources like data lake, HL7 messages, or any other data source. And the main feature of this profiling is the statistical analysis, which is helping us to have a detailed analysis on each field of the source data. To add more details about the statistical analysis, we are conducting different like type of analysis, such as the completeness ratio, the null ratio, the unique ratio, and the data type. If it's a string data type, some features about the length of that, or if it's an integer, some other analysis on that specific data type. And these analyses can help us improve our data mapping As an example, maybe when we look at the source data, we said that we wanted to map the patient gender to some specific FHIR target in the mapped object, but using our analysis, if that field is only populated 20% of the time, then we can immediately say that this field, even if it's a good candidate, but it's not a complete, and as a result, we can't map that to the source object. Or those statistical analysis can also help us to recognize our business identifiers and primary keys. As an example, if the unique ratio of one specific field across all the records within one object is 1, it means that that field can be a good candidate to be used as a primary key in the source object. The other feature that I really like is the field-to-field dependency analysis. And what do we mean by that is that like one specific test, as an example, A1C test can be stored in 2 different fields of the observation object. It can be populated sometimes in the as a coded value or sometimes in a text format. And using these field-to-field dependency, we can say that even if the coded value is only populated 70%, we can rely on the text format of that observation, that object, and then use them interchangeably when one of them is missing. And these field dependency using like heat map charts or other techniques can help us easily flag the fields that are dependent on each other. The other analysis is the coded value analysis, and that also is very helpful when we are working with codable concept data types in elements in FHIR, and it helps us better understand what systems are used across the source system. If it's like an observation, are they using LOINC, or if it's a condition, are we using ICD-10 or CPT codes for procedure? And using that coded value analysis, we can better find the distribution of systems in the source data. Lastly is that our automated profiling also represents some sample values for each field, which is also a good way of easily referencing and understanding the source data. And all of these features together as an automated data profiling helps us standardize our field analysis, detect keys and coded values, and also it produces a mapping insights across data sources, which is optimizing and improving the data mapping in general significantly. Now,
There,
yeah.
sorry, there is a question in the chat. Chris, do we want to save the questions till the end, or do we want to answer them on the fly?
Was planning to save them to the end, but if you've got
Okay.
time to answer them in the fly, and it's a good point, by all means, go ahead.
We may as well answer them here if we're in the context of this slide.
Yes, thank
So
you.
the question was, since the source data is going through the profiling SDK first in this diagram, are the key and value detections focused on when those keys and values do not follow the FHIR profiles? The quick answer to that is yes. So generally, if it's a very conformant FHIR API, there's not much of this business and primary key identification required, because we already know based on the FHIR definition where those keys sit. The discrepancies come sometimes when we've seen APIs that store this kind of key as an extension, for example, amongst a list of other extensions where we need to parse those and figure out what's what. And it's also very helpful, like Sari mentioned, sometimes we apply this beyond an API as well. So sometimes we're integrating directly with a data lake and transforming that to our FHIR schema. And there it's really helpful because often especially if the maintenance of the source database isn't perfect, they may not have mandated everything to be unique keys and things like that. So that's where it's really helpful to us when we see a whole bunch of numeric values in a data table. It's really helpful for us to be able to say, okay, this one is completely unique. As a result, that is likely a business key, versus this one might be, a set of SNOMED codes or something that is not quite as unique across the table. So things like that, it's really helpful for us to quickly identify those fields which are likely to be business identifiers. And then there is always a human step, of course, of validating that as well.
Yeah, and to add on, Graham, your answer, I remember that for one specific EMR, when we were looking at the observation object, we usually expect that the ID of the observation object to be a unique identifier for that specific resource, but we've noticed that there are lots of redundancy between the observation ID, and that was very helpful for further analysis and flagging the issue to the EMR.
Yeah. So we've actually used this to flag issues in source APIs that then the source vendor can go and address as well. In that case, it was actually the idea of the diagnostic report being populated across the observation IDs. So again, some of those little things that you don't really think of when you see a good looking or a nice looking FHIR output, but doing this analysis is really helpful because it finds those things very quickly, as opposed to if we were to just have blindly trusted that integration, it would have led to issues down the line when we started to ingest large amounts of data. So, okay, sorry, I interrupted there, but it was a good question.
Yeah, thank you, Grant. So the last step in our automated data profiling is how we wanted to make it transparent to non-technical people. And basically what it's shown in this slide is the way that we're documenting and keep track of our data lineage along with the logic and transformations that we're applying in our mapping process. So in the screenshot shown on the right side of the slide, we see that the details of the mapping in terms of what's the source field, what's the data type, and some of the statistical analysis that I mentioned previously in terms of the sample count, the unique ratio, completeness ratio, and some of the sample values. And then on the other section of the there are detailed view, we can see what's the FHIR resource and what's the FHIR element which we are mapping to them. Another feature is that it's also can show the candidates for natural language processing. We're not going into details for that specific feature on how we're doing that, but if you're interested in, you're more than welcome to join our colleagues called Cho, which is happening tomorrow, I believe at 2:40 p.m. And what we wanted to highlight here is just to show that how we're tracking of our data mapping, but what really matters is not the way that we're documenting it, it's just the insights that we wanted to get out of those mappings, and we make it transparent as much as we can to the end user and non-technical user. So that was all about the automated profiling and our integration platform. From here, I pass it over to Graham to continue the presentation.
Awesome. I do see a few more questions popping up in the chat. I think maybe let's leave those to the end, especially if they're starting to flow in a little bit more quickly now. Okay, so Sari's kind of gone over how we do that automated data profiling, how we present it back to people, maintaining that data lineage throughout. That document is accessible at any time. So if somebody has questions about why is this value appearing in this field, we can actually go back and see from our analysis, why did we make that mapping decision, and what is actually, or where is that data coming from in the source EMR, so we can identify very quickly, is it a user issue where they've entered an invalid value in a field, or did we actually incorrectly map that and we need to go back and make an adjustment. One of the most important outputs of that whole process, in my opinion, is now going to be the ability to automate the actual mapping step. So anybody that's worked with FHIR data recently or even not that recently will know that the mapping step is, even if you have all these metrics available to you, it's still quite onerous, and it generally requires somebody to go through every individual field in a source spec, identify what it contains and make sense of it, and manually map it to a target spec. So in our case, what we're trying to do with these outputs now is to actually automate that step using AI-powered schema matching. So this is a feature, it's still in beta for us. But the idea here is that now that you have a statistical representation of your source API, we can actually start to make suggestions based on the contents of a field, its completeness, what we know to be our target definition. So because we always map to a consistent spec, we can provide a lot of information about the typical profile of a field that we've mapped before. And in doing so, we can actually automate a good chunk of the mapping process, understanding that there's always still going to be the need for human review. But it's a lot easier to look at something that's already been mapped and make a decision and confirm it versus have to go through that extra step of figuring out what should this map to and mapping it yourself. So this is kind of a high level view on the right of how our scheme matching works. The first thing is, again, we start with a source schema and a target schema. The source schema is generally unknown. The target schema, we know, and it's a standard definition based on the FHIR resources that we support in our data model. When we get access to a source schema, we typically start to ingest a representative sample. So that might mean 500, 1,000 samples, 4,000 samples, whatever we deem to be representative. We feed that into a schema matching algorithm, and from there we can start to develop matching candidates. So the field statistics, along with other things like the field name and other descriptors, are fed into a featureizing algorithm that kind of creates embeddings that represent the fields in a vector space. Those embeddings are fed to a semi-supervised learner. There's a continuous training loop where it continues to see the input from end users, see other data that's been mapped and is continuously flowing in. And that semi-supervised learner creates a match score. That match score is presented back to end users through suggested mappings, where they can take a look at confidence, they can take a look at the underlying data that fed that suggested mapping, and provide input as to whether they think that mapping is correct, or they can also update that mapping if they think it's made a mistake. And like I mentioned, our matching algorithms continuously learn from that input. So it's kind of a self-feeding cycle and something that we're using to hopefully down the line speed up this process and be able to validate, even when we get a new instance of the same EMR that we have to integrate with, be able to quickly validate that the existing mappings are correct and that we don't need to make any updates based on how that user or that clinic uses the EMR that they have. So what has this led to, all this work? The first thing already, even without schema matching, we're seeing significantly reduced data mapping times when we're starting to stand up a new integration. Before this work started and we were doing mappings manually, this process of getting access to a source system's APIs or backend data tables, generating the mappings that are required, generating the queries and starting to pull that data into our system would take months, right? Especially for a large health system. Most recently, we've been able to turn that time from months down to days. I think actually the most recent integration that I worked on personally, using these tools, I was able to complete the profiling analysis in around 8 hours, meaning we can actually very rapidly integrate with some of these new EMRs, even if we've never seen the API before. Second of all, it's also given us a better understanding of the data gaps. So as we mentioned, the goal of integrating all this data into our platform is to use it for population health and quality improvement a lot of the time. And what that means is that this data is being aggregated and consumed. So you're not generally looking at individual records, but the completeness of individual records impacts the analysis that you're able to do downstream. And in identifying some of the data gaps in these APIs early on, we're actually able to address them because generally the data is there. It's just not where we expect it to be. So we're able to address them and increase the data quality in our database, which then leads to better analysis and more complete analysis downstream. And finally, it's provided more consistent data definitions. So we can now compare existing mapping or new mappings to the mappings that we've done previously in terms of their statistical makeup of the fields that we're mapping from. And that really ensures that what we're mapping into our target schema aligns consistently from EMR to EMR, integration to integration, and again creates a more consistent data set for downstream analysis and consumption.